Hello students, let us begin our next chapter, which is vibrations. So the students who are preparing for gate mechanical, this vibration will be studied as one of the chapters in theory of machines. And the students who are preparing for gate XC engineering science, and if you choose the XCD, okay, that is solid mechanics as your optional, then this topic will be studied as one of the subject itself, okay, in XCD. But if you ask me, what about this chapter? This chapter is like a subject only, because it is if you ask me an example with respect to theory of machines itself, this chapter is the combination of first two chapters. Okay, that much big chapter it is. That is, if you combine planar mechanism and analysis of planar mechanism, how much big that chapter will be, that much big this particular chapter is also. That is why if you take theory of machine subject, the first chapter, second chapter and this vibration alone will occupy 70% of the syllabus. The balance 30% of the syllabus will be the applications such as flywheels, rotating masses, balancing of rotating masses, gyroscope, governors and cams and gears. Okay, so all those 6 applications will fall under 30 to 35% only. And you might think, sir, if vibration is that much big, then why I need to study? Because it has huge weightage. In few exams, I'm talking about gate ME, okay? I'm talking about gate ME. In gate ME, in few papers, there used to be 2 marks. There are few situations, there used to be 2 marks. Or there used to be 1 mark and 1 2 mark. Or there used to be 1 2 mark. So compulsory 1 2 mark. Compulsory 1 2 mark. And maximum it can go up to 4 marks. That is 2 marks also possible. That is why this particular chapter is very important with respect to gate ME point of view. Even for gate XC point of view also, if you are writing XCD, then obviously this is one of the subject, right? Like their engineering mechanics will be one subject, that is rigid body mechanics, deformable body mechanics, and then you will be having vibration. So it is like a smaller subject compared to engineering mechanics and solid strength of materials. This is going to be a smaller subject, but still it is important. You might get some 4 to 5 marks from this also. I'm saying maximum, okay, maximum 4 to 5 marks. The majority of the weightage in XCD will be in engineering mechanics and strength of materials only. Vibrations will have less weightage, okay, because we know that XCD has 35 marks as a weightage, right? Out of the 35 mark, you can maximum expect 5 marks only from this vibration. So comparatively less. Strength of materials and engineering mechanics has more weightage. Okay. Now coming back to the subject, I said about its importance and all those things. Now, where to prepare? See, nothing. You just follow my lectures and then solve the problems which I'm giving you. Do the previous year gate questions, that will be more than enough. And of course, you need to attend the practice sessions and test series. Okay, so that will be more than enough for answering any of the questions. See, maximum 95%, I can guarantee you, more than 95%, in fact, more than 95%, whatever we are covering in our course, that is what they are going to ask in the exam. Nothing is going to be different from this. Okay, so you can believe me in that. Okay, so there won't be any issues. Okay. So now, before starting the subject, okay, before starting the topic or subject vibrations, we have to make sure that we understand few basics, okay, few basic introductory points. For example, what is mean by an oscillation? What is mean by an oscillatory motion? What is mean by a periodic motion or a periodic signal or a harmonic motion or a harmonic signal? What does mean by simple harmonic motion? Okay, what does mean by time period? What does mean by frequency? What does mean by circular frequency? All these things has to be covered first before going to the chapter itself. Okay, and one more point. All these things are basic physics. Okay, you would have studied in some 9th class, 10th class, 11th or 12th. I don't know the exact year where you studied, but you have already studied in your school level. I'm just revising it. But without this recollection of all those topics, if I directly go for vibration, then most of you will start blinking your eyes only, because without this, vibration is nothing. Okay, you need this introduction, and we need this introduction and basics to proceed discussing the complex topics from vibrations. Okay, so first let us start with what is mean by periodic motions or what is mean by harmonic motion. So before going into periodic motion or harmonic motion, recollect what are all the functions I will be calling it as a harmonic function. Do you able to recollect it? In trigonometry, if you take sine term, cos, tan, Okay, almost all the trigonometric functions are there, right? Sine, cos, tan, even, cosine, and all those things. Of course, not cosine, I guess. Yeah, even, not cosine, cot, and cosecant, and all those things. See, all those things are periodic functions, or we will be calling it as a harmonic function. Now, why we are calling it as a periodic function or a harmonic function? It is because, as per the definition of periodic function or a harmonic function or harmonic signal or periodic motion, whatever. See, all these are same only. In few applications, we will be calling it as a signal. Few applications will be calling it as a motion. Few applications, we will simply say it as a function. Okay, it depends. See, when there was any function or any motion which repeat itself after a particular period, then I will call that particular motion or a signal as a periodic or harmonic motion or signal. Okay. So what does it mean? I've given you an example here. See, you take sine, cos, tan, all this will have repetition. Okay, after some particular time, the function will repeat the same thing, right? So that is why any motion or any signal which repeats after some particular time period, I will be calling it as a periodical function or periodical signal, or what is that? Harmonic signal or harmonic motion. Okay, motion or signal, whatever way. Now, I'm taking an example here. You take some in y-axis. Okay, y-axis I'm taking it as x. This x can be a velocity, it can be acceleration, it can be jerk, it can be force, whatever, or displacement, whatever. Okay, I'm just taking in general x. That x can be anything. We will discuss about it, like how to find out velocity, acceleration, all those things one by one. But as of now, in y-axis, I'm taking some component. That component depends on time. As time varies, that component is going to vary. And also it depends on theta. So what is this theta and how this x and theta is related? You don't have to worry now. I will explain to you later. As of now, you forget about this. Okay, as of now, you forget about this. So as of now, I am plotting a graph between x and t. Okay, x is some component, maybe acceleration, displacement, or velocity or something, which is a function of time. And how it varies, as you could see here, x actually increasing and then decreasing, and it is reaching negative minimum, then increasing to the same value. So from 0, it reached to positive maximum, then 0 again, negative minimum, then 0 in a time period tp. And again from 0, positive minimum, 0, negative minimum, 0 in a same time period tp. So in the same equal time period tp, if the same pattern repeats, okay, if the same motion or the same signal repeats, then I will be calling it to be my periodical signal or harmonic signal or periodic motion or harmonic motion. I given you the definition also. Any signal or motion repeats after equal interval of time, it is periodic or harmonic. And if you take sine, I said that sine is a periodic, right? How it is? This is how it repeats, right? See, this is my time period there. Okay, this is my TP, after which it again repeats. Okay, Okay. So I'm just giving you an example here. So this TP is there, right? That is an equal time interval after which it start repeating is there, right? That time period, that TP is called as time period. And this is called as one cycle. Okay, this is my first cycle actually. This is my first cycle, or I will just write it as one cycle, okay? This is one cycle, and this is one cycle. Okay, this is one cycle. So time period is what? Time taken to complete one cycle. Okay, so when it reaches from 0 to maximum and again from maximum to 0, from 0 to minimum and again from minimum to 0. Okay, if when it completes, that is this component, whatever component, displacement, velocity, acceleration or jerk, whatever it is, when it completes this one complete, 0 maximum, 0 minimum and then again 0, that is called as one cycle, and the time taken to complete it is called as time period. Okay, so next, the term which I am defining here was time period. This is nothing but time period TP. Okay, time taken to complete one cycle. Okay, time taken to complete one cycle is called as time period. Generally, time period TP will be represented in terms of seconds only. So it is going to be seconds per cycle. Okay, for each cycle, how much time? Okay, seconds per cycle or just seconds per cycle. Okay, how much time it is taking for completing one cycle is called as time period. Now listen, take an example of shaft. Just giving you this example. As we move forward, we will be discussing many things. Okay, first let me take an example of shaft here. Okay, let us consider that the shaft is rotating with an angular velocity. Angular velocity, right? Omega. Or let me take n value. Okay, so n to be 3000 RPM. Okay, 3000 revolution per minute. Let it be. Okay, 3000 revolution per minute. If I want to convert it into seconds, what I will do, in place of minute, I have to substitute in seconds. So it is 60 seconds. So 3000 by 60 RPS. Okay, that is nothing but 50, right? 50 revolution per second. Okay, so when this shaft rotates, okay, at 50 RPS, what is my time period? How can I find out time period from this? See, 50 RPS means what? One revolution. If it completes one complete revolution, let us take it as a cycle, one cycle. When shaft completes one complete revolution, let it be a cycle. You will have more clarity about this, why I am taking one revolution as a cycle and all those things as we move further. Okay, now listen. So one complete cycle is one revolution. So it means it is completing 50 cycles per second. Okay, it is completing 50 cycles per second. So 50 cycles per second means, so how many seconds it is taking for one cycle? How many time it is taking for one cycle? Simply it is 1 by 50, right? 1 by seconds per cycle. So for completing one cycle, it is taking 1 by 50. 1 by 50 means what? 0.02. Okay, 1 by 50 means what? 0.02 seconds. Now listen, very important point. Increase this n to 6000. Increase this n to 6000. A very big increase, right? A large increase. That increase of the n value was very high. From 3000, I'm increasing it to 6000. What will happen to this? It will become 100. I'm just taking it as, it is 100. It will be 100 cycles per second. Now, what will happen to my time period? 1 by 100, which is 0.01. Second. So, if it rotates at 6000 RPM, which is actually a big number, we are getting time period 0.01. If it rotates at 3000 RPM, we are getting time period as 0.02. So how much difference I am seeing here? See, if RPM increases by a large value, my time period is increasing by very little value. Okay, very small increase in time period is happening, even though if there was a drastic increase in my rotation. That is why time period is something which is not a good factor for analyzing the subject or for studying the subject further. So for studying the subject further properly, see, you could clearly see it, right? There was a very small increase. See, this increase in the time, we can even neglect it also. 0.02 second, 0.01 second. That increase is very less. But reality is, the increase in RPM was something very high. From 3000, it is increasing to 6000. So it's like, even though there was a huge increase in n, the time period value was very small. The increase in the time period was increase or decrease, whatever the decrease in the time period was very small. So change in time period is very small. So it will be almost like it's no use in studying time period, or I couldn't use the time period effectively for my study. So what we will do, not we, actually Hertz did it. Okay, Hertz is a a researcher, scientist who did it. He taken a new term, okay, called as frequency. And he said that it will be F, okay, represented with F. So how much cycles, okay, the cycles which you can, the cycles which can be completed, okay, cycles completed in 1 second. Okay, or I could say that cycle completed per unit time. Okay, cycle completed per unit time. That is called as frequency. Okay, and how to find out this frequency? F is equal to 1 by Tp. Simply the reversal of time period will give me frequency, and what's going to be the unit? See, time period is how many seconds it is taking to cover one cycle. This is how many cycles and I can cover in 1 second. Okay, how many cycles I can cover in 1 second. So cycles per second. Or this cycles per second can be called as, Hertz. The researcher's name itself. Okay, since frequency is a term which is formulated by him for just to make him proud, we are naming cycles per second as Hertz. Okay, Hertz, HZ. Okay, so you can represent fully, or you can simply represent with Hertz also. That simply means how many cycles. Okay, how many cycles per second. So let us discuss about what is that. Let us further continue our discussion in periodical motion. Okay. So so we know that this is our periodical motion, right? Example for a periodical motion: any component x which repeats the motion for a fixed time interval, right? Let us, for the each time interval, time period, if it repeats, okay, then I can call it as a periodical motion. Now, what Hertz did? Okay, what Hertz did was, he said that a periodical motion or an harmonic motion, whatever, can be represented, or the motion, the periodical motion, is something which is similar to, okay, something which is similar to a particle, okay, something which is similar to a particle, which is, okay, this is the particle, okay, this is the particle which is present at an angle theta from x-axis in anticlockwise direction. So motion of the particle in a circular motion, okay, circular motion or a motion of a particle in a circle with a constant angular velocity. So he said, or I could say that it's an analogy which Hertz have framed, that a periodical motion can be represented as a particle which is moving in a circle with an angular velocity omega. I will make you to understand this in a better way. How? Listen. See. Let us consider, we have to understand it in a different way. Okay, this is uniform circular motion. See, what is mean by uniform circular motion? Just a moment, okay. So, uniform circular motion, Hertz said that periodical motion, any periodical motion, you take any periodical motion, that periodical motion can be analogous to, okay, it can be analogous to, it can be similar to uniform circular motion of a particle moving in a circle with a constant angular velocity. Uniform indicates constant angular velocity. Now listen, how he framed this analogy. Let us assume, let me represent this. A particle is present here initially. Okay, a particle in a circular motion, it is present at this extreme. And when it comes to this case, let us take the particle is present here. Okay, as the particle moves, see, you could clearly see that if I simply project here, okay, if I simply see from this direction, this particle will be present here. Simply if project it, okay. As the particle starts rotating with a constant angular velocity, as it is starting rotating in this circular motion, this particle will start moving here, okay. So when this reaches here, okay, this is the point. This particle will reach here, this particle will reach here, okay. And further it moves, this particle will reach here and this particle will reach here. And this particle further moves above, this particle further moves in this direction, and it will be reaching at the topmost point, and this will also reach the topmost point. I hope you are getting. Initially it was at the bottommost point, it was here. And it start moving in this direction and it start increasing. This is also start increasing. It reached the topmost point. This is also reaching the topmost point. Now it starts decreasing. Okay, let us consider it has reached somewhere here. Okay, it is here. Okay, further decreases. It reached here. It's here. Okay, further decreases when we reach here. That is when we reach 0. It was at the leftmost point. Again, it is also in the x-axis only. Okay, it is also in the horizontal axis. Now further it decreases in negative direction. It is also decreasing in the negative direction. You could see when the particle reaches here, the particle is going to be here. When the particle reaches here, the particle in the circular motion is going to be here. When the particle was here, it will increase and it will be here. And finally when it comes back at this position, the particle will be here. So when the particle completes, okay, when a periodical motion happens in one cycle, okay, in one cycle, when the periodical motion completes a single cycle, okay, not until here, okay, until here, okay, until here. When one cycle of a periodical motion completes, a particle rotates in a circle with angular velocity, with a constant angular velocity for one revolution. Okay, particle undergoes one complete revolution in a circle. Okay, with a constant angular velocity when one cycle of periodical motion gets completed. When one complete cycle of periodical motion happens, what is happening to theta? Initially theta was 0, Okay, the particle was at 0. It's increasing, reaching to theta 90 degree. Theta becomes 90 degree means my particle will be here. So at this position 90 degree. At this position 180 degree. At this position again 270 degree. And here it will be 360 degree, or other words 2 pi. So when this particle completes 2 pi distance, that means 1 revolution, I am able to complete 1 cycle in the periodical motion. And this is how Hertz related it. Hertz said that how a periodical motion is happening, that I can compare, that I can make an analogy, okay, with a particle which is undergoing circular motion with a uniform angular velocity. That's it. This analogy will be very important as we proceed discussing further. Okay, so when this particle completes 1 revolution, this 1 cycle of a periodical motion is happening. Okay, this is the key point which Hertz said. And more importantly, the particle was moving in a circular motion with a uniform angular velocity. So it's a uniform circular motion. Okay, now listen. As I said that the particle is undergoing uniform circular motion, we know one thing. What is that? We know S is equal to ut plus 1 by 2 at square. From the basics, in terms of angular, I can write theta is equal to omega, initial omega, right? So omega naught into t plus 1 by 2 into alpha t square. We know omega is constant. We know omega is constant because uniform circular motion, right? Omega is constant. If omega is constant, what is going to be alpha? Alpha is nothing but rate of change of omega, so alpha will be 0. If alpha becomes 0, my theta will be simply omega into t. Omega naught is omega, right? So omega into t. Omega naught will be same everywhere. So theta is equal to omega into t. Theta is nothing but what? Angular displacement of this particular particle P. Time is what? Time is nothing but that time t, which I am representing it in x-axis. Okay, so here you could clearly see theta is proportional to t. Since omega is constant, theta is proportional to t, and that is the reason why. That is the reason why at the beginning of this lecture, when I was starting this periodical motion lecture, that time I said instead of t, I can use theta also in x-axis. As we proceed further, we can use theta or we can use t in x-axis. Okay, right. So now there is one important conclusion. We know when this particle undergoes one complete revolution with a uniform angular velocity omega in a circle, during that time when it completes 1 revolution, my 1 cycle of periodical motion will happen. So 1 revolution of a particle moving in a uniform circular motion will be equal to 1 cycle of my periodical motion. 1 cycle of my periodical motion means what? 1 cycle of my periodical motion means what? Time period. The time period taken to cover it was Tp, right? One cycle means the time period which is taken. Okay, it's like equivalent. When this particle covers 1 revolution, my particle in the periodical motion covers 1 cycle. Okay, so how much time it is taking to cover 1 cycle? It is taking Tp time. And how much angle it is covering? 2 pi. Okay, so for covering an angular displacement of 2 pi in a circular motion during the time, let me repeat it again. I'm sorry, let me repeat it again. During the time when this particle, covers 2 pi radian, okay, during the time when this particle covers 2 pi radian, which means 1 complete revolution, this particle covers 1 complete cycle. So can I say when theta is 2 pi? Can I say when theta is 2 pi, my time taken to cover will be Tp? Let me repeat it. This particle it's covering 1 revolution in the same time when 1 cycle of this periodical motion has happened. So 1 cycle of this periodical motion has happened in a time period Tp, and what about my theta? My theta was 2 pi radian. So in place of this t, I can substitute Tp. In place of this theta, I can substitute 2 pi. So if I do substitute it here, 2 pi will be equal to what is that, omega, right? Omega into t, and this will give me omega is equal to 2 pi tp, omega 2 pi by tp. Very important formula. Okay, this omega is there, right? I will represent it there so that I will have some space. This omega, which is equal to 2 pi by tp, omega which is equal to 2 pi by tp, and this omega is equal to 2 pi by tp is nothing but your circular frequency or circular natural frequency. I'll come for it. But before, for the same conclusion, conclusion which we got from theta is equal to omega t, I can get it from one more way also. What is that? F is equal to 1 by tp, right? Tp cycles per second. Okay, so how much cycle it is taking to cover? 1 second. Now for covering one cycle, how much revolution it is? See, I can replace one cycle in terms of one revolution. One revolution means 2 pi radians. So if I want to replace this cycle in terms of radians, can I replace one cycle is equal to one revolution, which is equal to 1 radian? Simply, one cycle in periodical motion is equal to 2 pi radian in the circular motion. So in place of one cycle, I will simply replace with 2 pi radians. Okay, 2 pi radians. Okay, so 2 pi by tp radians per second, and when I represent in terms of radian per second, I need to use omega. Same conclusion what I got here. Okay, this is one of the way. To end in the same conclusion. I will stick with the same way. Okay, so theta is equal to omega t. When the particle covers 2 pi distance, in my periodical motion, it is covering one cycle. Okay, so one cycle, whatever the time period is taken, the same time period it will take for this particle also to cover 2 pi radian. So in place of t, I am substituting tp. In place of theta, I am substituting 2 pi. So I end up with omega, and that omega is called as circular frequency or circular natural frequency. And I can write this in one more form. What is 2 pi into 1 by tp? What is 1 by tp? This frequency, right? So simply I can write it as 2 pi into f also. So omega, which is equal to 2 pi by tp, which is equal to 2 pi f. This is simply circular frequency or circular natural frequency. See, you might have a doubt here, sir, why natural? And I will be representing it with omega n. Why natural? Why omega n? You will understand it in detail once after starting vibrations. Okay, we have not yet started vibration. I'm just giving you the introduction, basics which is required to start vibration. Okay, basically this natural indicate the vibrations are happening without any damping. There is no restriction. It is freely vibrating, naturally vibrating. That is why this natural indicates. You will understand it once we classify the vibration and all those things. It takes some time before we will understand the basics. Okay, what is the one more point I want to say? Why it is circular? Because I am representing in terms of radian, right? I am representing in terms of radian per second. That is why circular frequency. This is just frequency. I will represent in terms of cycles per second. Okay, so we have one more term to understand, that is amplitude. Okay, that is amplitude. I will represent it with A. Okay, so what is this amplitude? Amplitude is simply the maximum deviation. Okay, it is the maximum deviation from its mean position. Okay, from its mean position. I will show you in the graph so that you will understand it better. Okay, see, for this particular case of periodic motion, we have this as our mean position, and from mean position, this is our maximum, right? And it is in positive plus A, and this is minimum, so that is going to be, I will write it here. Okay, this is plus A, and this is minimum, that's going to be minus A. So from maximum to minimum, there was variation in the amplitude. Okay, so this will be either you take it in this direction, you take it in this direction as A, or in this direction, whatever, the magnitude is going to be A only. From its mean position, wherever the maximum it reaches, magnitude is going to be A only, but the direction varies. As it is coming to the bottom side, I will have minus A. If it is top, it's going to be plus A. Okay. Now listen. Amplitude means you might think that, sir, does it related only to displacement? No, it's not. It's not true. See, x here doesn't mean that it is only displacement. For an example, I've taken it as x, but it can be x, or it can be velocity, it can be acceleration, it can be force also. So amplitude, we can calculate amplitude for a displacement. Okay, when it comes to displacement, I will generally use x naught for representing the amplitude, or A. Okay. If it is velocity, okay, if it is velocity, x naught dot, okay, or V simply for representing amplitude of the velocity. If it is acceleration, okay, if it is acceleration, again 2 times differentiation of displacement, right? 2 times. This is 1 time differentiation, so x naught dot. So 2 times differentiation, so this is x naught double dot. Or we can represent with small a, okay, acceleration small a. And finally force, simply I will represent with f naught. Okay, so amplitude exists for all displacement, velocity, acceleration and force. In the example, I'm just taking it as x, but it can be the y direction, can be anything. It can be amplitude, it can be displacement, velocity, acceleration or force. Okay.